Welcome to Environmental Systems Dynamics and Modeling. Today we're going to discuss some examples of environmental models that will allow us to create our own models and will allow us to know some commands and functions that can be used for dynamic systems. So far we have discussed examples that are related to population dynamics, to mass and energy balances, and to climate change in general. So now we're going to focus on biochemical and biological transformations, and also we're going to have an example on logistic row equation that can allow us to know how to set up not only a numerical solution through the Euler method, but also through the functions that are embedded on Matlab. Now we're going to set an example of how to start with a Matlab script. So we're going to follow the same example that was previously discussed on the chemical and biological transformations. This is the generation of acid mine drainage, and we, as stock flow equations, we have the mass of the hydrogen produced that decreases the pH in the system, and that is the problem with the acid mine drainage generation. And the generation is driven by pyrite oxidation. So we have our, we're gonna follow we're gonna create a Matlab script from these stock flow equations. We're going to focus only on the hydrogen, the stock hydrogen, and therefore we're going to use the flow equations related to this. So the flow equations that we will use will be the hydrogen produced, that is the inflow, and it can be as shown in the left side on the diagram on the left side. It can be calculated by looking at the consumption times the yield, or we can also directly relate it to the rate of oxygen transfer, which this is what we will do, and times the yield. As outflow, we have the hydrogen that is leaving the effluent, and this is calculated by the mass of hydrogen in the stock divided by the volume, times a flow that it is the excess of water that is leaving the system. So as you can see, this means that the effluent is an algebraic variable because it involves the stock. So additional equations that we need to consider are the rate of oxygen transfer, and that is driven by the film transfer coefficient, the area, and the saturation of oxygen, right, in the system. The difference between the concentration of oxygen at saturated conditions and the concentration of oxygen that is considered to be 0. So this is how our Matlab script is being organized. We mentioned before, we can start with the initial values, and in this case we have the film transfer coefficient, the surface area that is constant in our case, and the oxygen transfer that we can call it the oxygen saturation at saturating conditions, and we can call it O2. Then we have the numerical parameters. We need the time to simulate, the time step of the simulation, and we also need the total number of steps to simulate. Okay? Then we can create a solution time domain. This will be equal to, this time domain will go from 1 till the final time, right? And then we also we will need to generate to round each element of the time to the nearest integer, and for this we can use the function, the command floor. Okay, then we can continue writing the initial conditions, and in this case we're dealing only with one stock, so we will need the initial condition of this stock, and that will be M1. Then we will have to array. We can use also we can generate a matrix or solution domain, which is the size of the matrix, right? So we can already generate the space that the information will be added, right? It will be automatically populated. So this is the stock, which is equal to zeros, and then this will be the size of this matrix will be defined by nt rows and one column. Then we have the equations. These equations are not the algebraic equations, as I mentioned, because algebraic equations must go within the model solution. So the equations that we will go are equations that are fixed, do not change over time, which in this case will be the yield and also the transfer, the rate of oxygen transfer. Then we will have our model solution, and to get the model solution we will create a for loop. All right, what do we want to say in the for loop? We want to say that the solution will be to get a solution, the model will run from time equals to 1 till nt, which is the final number, the number of time steps minus 1. This means that it will iterate from start until calculation of last solution step. And then we also need to generate we need to create our equation, and our equation following the Euler method format will be the stock time plus 1 will be equal to the m at previous time. That's why we need the first value of m, as we have done that before when we write the initial condition, plus the inflow and outflow times dt. That will constantly update the stock. And to update the algebraic variable, and what is this algebraic variable? It will be the effluent, right? Because that is our algebraic variable. This algebraic variable will be calculated at each time step once we have the first solution, the first time solution at time 1. And this can be equal to t plus 1 equals to k times the stock times the yield. And then we need to end to finish the simulation calculations, and then we need to visualize and analyze the solution. This can be done by providing a way of making plots and a way of making tables.